Again, welcome everyone to the 127th meeting of New Directions in Crypto and Geometry Categories. Our speaker today is Anish Chedalavada from Johns Hopkins, Baltimore, and he'll be talking to us about Zariski geometry.
Hi, thank you for the invitation. So let's go ahead and get started. The title of this talk is Zariski Geometry. That's also the title of the paper that it's based on. And today I'm going to basically begin by trying to motivate a little bit of the setup behind what goes on in this paper. So specifically what this word means and as a loaded term. Okay. So let's start with thinking about classical algebraic geometry. So classical AG, say we're working with varieties over C, so very classical. We deal with objects that look something of the following form. So topological spaces that looks locally something like intersections of vanishing loci of polynomial functions in affine n space over C and non-vanishing loci of polynomial functions. So our basic objects look something a little bit like this, an open and a closed subset. And our object M carries a sheaf, OM, and that's a subsheaf of the sheaf of continuous functions into C. Here I'm regarding everything with the Zariski topology. And what OM exactly does is it corresponds to the rational functions. So on an affine neighborhood, so let's call these things affine opens. So these are affine objects. And on affine neighborhoods, it's a rational function. It's a rational function with poles outside of my affine neighborhood. Okay? Now, maps between varieties are going to be pairs. They're continuous maps between the topological spaces M to N. And they moreover satisfy the following condition. If I precompose with my continuous map phi, I get an induced map between these sheaves of continuous functions given by, so this is to be regarded as taking place in sheaves on N, sheaves on N, coefficients in commutative algebras. Recall that this is sort of by definition the push forward of Cm blank coefficients in C. And so what you demand is that this precomposition with phi restricts to the subsheaves On to phi star On. Concretely, what that says is that precomposing with this continuous map precomposing with this continuous map on affine open neighborhoods sends rational functions to rational functions. It's the same condition that shows up in differential geometry with smooth. And because this is a local condition relative to affine opens, we can phrase it sheaf theoretically. Okay? And the point is that maps from some variety to an affine patch is very easy. Concretely, if I want to give myself a map from my variety M to an affine patch that looks like the vanishing of some ideal intersect some non-vanishing locus, then that's just giving me a map to ANC, which is a choice of n polynomials mapping into which is a choice of n rational functions on M, n globally defined rational functions on M, which is just a map from this polynomial ring on n variables. And to give me the data of having factored through this locus, I just had to give me the data of having mapped through the quotient by I2 and the inversion by G2. So maps to affine patches are easy, and this undergirds the basic feature of algebraic geometry, which is that mapping to affine patches are solely determined by maps on global sections. Okay, so one thing that's maybe undesirable about this setup is that the way that I've presented it, I've introduced this auxiliary gadget, which is continuous maps into C. And oftentimes I don't want to be fixing my base field. Maybe I want to work with polynomial functions that are defined integrally, in which case I want to study their solutions over FP. And it's helpful to not have to refer to these things separately. And so intrinsically, my allowable maps from M to N are almost just pairs of a continuous map from M to N and a map of sheaves from On to the push forward of OM. in the category of sheaves. What goes wrong if I just give myself an arbitrary map like this? Well, if I give myself an arbitrary map for a continuous map from M to N and this precomposition map between their sheaves, what could go wrong is a failure of locality, right? So there could have existed an f that was a rational function defined on some open neighborhood U, such that at some point x, f was in the ideal of functions which vanish at x, but the map that I selected sent f to something that was invertible on a point in the preimage of x, which is bad because if it was 0 on x and my precomposition was invertible at a point before x, the putative rational function that it was supposed to be was not defined. I would have had to define, I would have allowed myself to divide by 0. And so this could not have come from an allowable map from M to N. And so concretely, what I need to rectify this is I need the following notion of locality. I need it to be the case that if I look at the image of the locus where this precomposition of f is not 0, where here what I mean is every point where it's invertible, every point where it's invertible, yeah, I mean that disappears, but yes, every point where it's invertible, I need the image of this thing to have been contained in the locus where f is not equal to 0. Okay? So it's a support theoretic condition. Concretely, a sheaf of rings gives me some support theoretic condition on where the elements of that ring don't vanish, and I need the supports to play nicely. And so there's two ways to formalize the kind of category that you're working in, right? So to rectify this, of course, you just disallow maps like this, right? You work with local maps between M and N, where you disallow the maps between sheaves to invert elements on the stalks. And what you get is a category that ends up recovering what you want. And there's two ways to formalize that category that you're working in. The pointed formulation speaks to what's going on at points of the space that you work with, and that's locally ringed spaces. And it's this classical notion due to Grothendieck and maybe Zariski. And what I'm going to talk about today is this point-free formalization, which doesn't make reference to points. And it's this notion of geometries, which Lurie introduces in DAG V, maybe with precursors in work of Monique Hakim. So let's talk a little bit about how the setup is supposed to go. So given a topological space X, there's an embedding from the category of sheaves on X into the category of functors from commutative algebras op into sheaves on X. Here I'm leaving this unlabeled to indicate that I mean sheaves valued in infinity groupoids, but if you don't like that, then you can think of sheaves valued in sets. None of this setup is sort of contingent on working higher categorically. But yeah, so the undecoration is just, valued in your base category of interest. And what does this do? This sends a sheaf F to the assignment that sends a ring to the sheaf of ring homomorphisms from R to F. And what does this do on U? It's exactly, HOMs from R into FU. Okay. Again, I've left it undecorated, but I mean HOMs of rings, right? So this is an instance of Yoneda philosophy, right? You can just check that this is an embedding by checking it pointwise, essentially. And you can identify what its essential image is. The essential image of this map is exactly essential image is exactly the colimit preserving functors, or the limit preserving functors, I guess. So it sends limits in CalJob to limits in sheaves X. And so you can say that you can identify sheaves X calj with functors, left exact functors, so finite limit preserving functors from calg omega. Okay, let me move everything down so we have a little bit space. So left exact functors from calg omega opt, the compact objects of commutative algebras, to sheaves X. Okay. Of course, because every commutative ring is a filtered colimit of compact objects, and so everything is sort of reduced to what's happening on compact objects. And I will say that a functor from compact objects of commutative algebras to sheaves X is a local Zariski structure. If for every Zariski cover of R, so map from R into a product of rings, R into a product of localizations where I've localized at a collection of elements who jointly generate the unit ideal, I demand that the map O, the induced map O R F I inverse to O R be an effective epimorphism. An effective epimorphism is, it is like an epimorphism. It just means that, like, the kernel pair, actually, like, this thing is an equalizer of the kernel pair. Higher categorically, it's kernel diagram. Okay, what is this actually saying? For a variety, if you gave me this thing OM, what this says is that for any R in commutative rings, with a cover like so, RFI inverse cover, that the map HOM from the disjoint union of HOMs RFI inverse into OM is an effective epimorphism onto HOM ROM. So concretely, I have, if you give me an open set of my base M, then this maps like this, pick out a map from R to OMU. And a lift this way is a map from R to OMU, which factored through some choice of RFI inverse. And the fact that this map is an epimorphism in the sheaf topos, or in the category of sheaves on X, what that's concretely saying is it says that the union of all the loci where Fi is not equal to 0. So when I say Fi is not equal to 0, I essentially mean the loci where I factored through something that where I factored through a localization, right, in this map. The union of these loci is actually and here I'm regarding this in U is actually just equal to U itself. So for any open set, I had for any open set, if you gave me a collection of rational functions, Fi, F1 plus Fi, which sum to a unit, let's say, which equal 1, then it should not be the case that if I intersect all the places where they're equal to 0, that this is non-empty. Because if I intersect the places where they're equal to 0 and that's non-empty, then at that point, 1 should have been 0. And this was bad, right? Or if this were a unit, for example, if this were an OMU cross, then if there was a point X in here, at this point, this unit U would have been equal to 0, would have vanished. And so I would have a rational function that's defined here, which should not have been defined here. If you think about what's happening at a point at a stock, this concretely says that the stock had to be a local ring, and you can sort of unpack this condition for a stock and see that the stock is concretely has to be a local ring. Okay, awesome. So that's what it means to be to admit local Zariski structure. Now let's talk about what it means to be a local map. A local map from XOX to YOY is going to be a pair Y to X of a continuous map, and phi sharp from OX to phi upper star OY. And moreover, we're going to demand it to satisfy the following, given a Zariski localization R to RF inverse, I demand that the following is Cartesian. And so I have my assignment OY RF inverse mapping to OY, and this receives a map by adjointing over. I get a map from phi upper star OX to OY. And so I get a map from phi upper star OX to OY evaluated at R, and I demand that this is a pullback. Okay. What is this condition saying? This condition is saying that if you give me a map of varieties, right? If I look at Hom and you give me and pick a ring as above, that Hom R, the sheaf Hom RF inverse ON mapping to the sheaf Hom R ON. This receives a map from Hom blank R by lower star OM. And this sits in a pullback diagram. Blank RF inverse phi upper star OM, or phi upper star OM. Okay, what is this saying? To produce a map here is to give me a map from R to ONU. To produce a lift here was to provide me, let's do that in a different color actually. To provide me a lift here was to give me a factorization through RF inverse. And concretely, this says that if I look at the essential image of, if this actually lifted to a section on an open neighborhood of the image, so a map here is the same thing as a map from R to OMU, or OMV, where V is a neighborhood containing phi of U. That any lift here would have necessarily had to have existed here as well. Concretely, what it does is it encodes this locality condition that I brought up upstairs. Concretely, I needed this locality condition to hold. And that's what this condition encodes. Okay? So this is the category that I want to work with. The category of spaces with local Zariski structure. Denoted top-lock couch is the category with objects given by pairs of X a topological space and OX in sheaves, or let me say it like, let me write the other way. Fun left exact from Calge omega op to sheaves X, a local Zariski structure. And the morphisms are exactly given by morphisms X XOX to YOY, which are local morphisms in the sense above. Okay. And the theorem, which I'm going to gray
I have a
out.
question.
Mm-hmm.
So this top lock couch, I mean, you're studying it as a what category? As a infinity one?
Infinity category maybe I should yeah, I should be careful and say infinity category. Again, I'm being a little agnostic here because strictly speaking, none of this is contingent on working in the higher categorical setting. Everything that I said could work with ordinary rings as well. So that's why I'm being agnostic, but maybe I'll gray out infinity category to indicate that it could have been higher categorical, and that when I said calge, I could have meant E infinity rings. Later I'm going to disambiguate that.
Thank you.
Okay. So the theorem, which I'm graying out the attribution to Lurie to, is that there is an adjunction of the form gamma top law calge to calge up, which is this global sections spectrum adjunction. For R and calge, spec R is the pair of the Zariski spectrum. So it's the Zariski spectrum of R. And the sheaf, which sends a basic open DF, to RF inverse. Again, I'm writing this as a sheaf, but the point is that any sheaf of commutative rings corresponds to a left exact functor from the opposite of compact commutative rings into the sheaf category via this embedding. And so I can afford to be a little bit abusive with notation and say that this is what I really mean. And the point is that this is actually a local Zariski structure. And the grayed out attribution to Lurie is the fact that actually this could have worked with E infinity ring spectra instead, and is the basic setup for how you might set up spectral algebraic geometry. With this as your basic with Zariski spectra as your basic objects, right? And in the infinity ring setting over here, you replace this with spec pi 0 R. Okay. So now let's move on to geometries in general. So Lurie in DAG 5 actually, does something much more general and explains how this setup is a generic feature of any category with a small amount of structure. And so the amount of structure that I had to specify on calge was the data of exactly what open inclusions were supposed to be, which were principal Zariski morphisms, and covers, which were Zariski covers. And so more generally, Lurie makes this definition of a geometry. A geometry is a small infinity category G, which satisfies two conditions. It admits finite limits, and it's idempotent complete. And it's equipped with a wide subcategory. Wide means it contains all of the objects of G, of admissible morphisms. And we demand three conditions of these admissible morphisms. First, we demand closure under pullback. So the pullback of an admissible morphism is still admissible. Read that the push out of a Zariski localization is still a Zariski localization. Closed under left cancellation. So if it's a 2 out of 3 condition, if this is admissible and this is admissible, then this is also admissible. And it's closed under retracts formed in the arrow category, which I'm not going to draw a diagram for, but it's an easy technical condition. And finally, you demand a growth-unique topology generated by admissible morphisms. So you require the covering sieves to be generated by a collection of admissible morphisms, basically. So let's do an example. The classical Zariski geometry on, grayed out E infinity rings is given by G Caesar, where this is the category of, compact commutative algebras op. So this is almost a finite presentation. So finite presentation, then you close under idempotent, close under retracts. The admissible morphisms are exactly localizations of this form. Here, for the infinity version, you ask for F to have been in pi 0 R. And tau, the covering sieves exactly contain these covering sieves are exactly those which contain these collections of morphisms, right? So R mapping to a product of Zariski localizations, where the things that you localized at jointly generate the unit ideal. And the key definition of our paper is the Zariski geometry on 2 rings. So what is a two-ring? A two-ring is the infinity category of two rings is this category. So calg and catperf. What does this mean? These are the categories which are stable, which are stably symmetric monoidal. So that means that the tensor product is exact in both variables, and idempotent complete. This is an enhancement of the notion of triangulated categories. So this is an enhancement of triangulated categories of TT-cats. And the Zariski geometry on two rings is given by three pieces of data. First, GZAR is given by the category of compact two rings up. Second, we ask for the admissible morphisms to be these principal Karoubi quotients. Karoubi quotient is, I think, nomenclature that's introduced in the second nine-author paper, Hermitian K-theory for stable infinity categories. And it's a Verdier localization after which I apply idempotent completion. The covering sieves exactly contain these products of Karoubi quotients where the kernel is contained in the nil radical. So it consists of tensor nilpotent objects. You could ask for a variation where you didn't actually demand this and you asked for the kernel to actually have been 0. And then the theory works fine and you can set up the geometry just fine, but the spectrum itself isn't identifiable and doesn't fit a comparison to the Balmer spectrum. I'm kind of hoping that there's a condition that reads what it means to be a thick tensor ideal that's more in the language of what's going on here, where they jointly generate the unit object. Because again, what are these guys? These are exactly, if you were looking in two rings, these are exactly Dirac localizations where the target is also stably symmetric monoidal, and then you ask for idempotent completion after the fact. So if the Zariski topology for rings talks about inverting elements, then a two-ring is like a ring with many objects where I talk about inverting morphisms. And so this is one reason why you might call it the Zariski geometry and not the two Zariski geometry, because you're doing the same thing in some sense. Okay. So now what's the point of a geometry? The GP of geometry, the infinity category of infinity topoi with G structure, we're no longer working with spaces, but let me explain what this means. So X is a pair of an infinity topos. What's your basic example of an infinity topos? Think sheaves of infinity groupoids on a spaces. So your basic example is always going to be something of the form sheaves X. And maybe the reason for working in this generality is that you might, want sheaves on an arbitrary frame or potentially sheaves on a different growth and decay site. And if there's time later in the talk, we'll talk about some ways in which those show up. But for the moment, if you prefer to think of infinity topoi as like containing spaces as a full subcategory via assigning a space to its category of sheaves, then that's also perfectly fine. It's given by pairs of X and infinity topos and a left exact functor from G into X. And moreover, we demand that O do satisfy the same locality condition as above. So O sends admissible covers to effective epimorphisms. The exact same condition as I saw upstairs with Zariski structure. And the morphisms are also going to be the same. My morphisms are now going to be they're happening in L top, so I'm doing the opposite of the geometric direction. They're going to be pairs of a left exact. So this is going to be a left exact left adjoint. Again, your basic example is always going to be, given a continuous map of spaces, look at the pullback functor from sheaves y to sheaves x. And the morphisms are going to satisfy the same locality condition. And what's the locality condition? If you give given satisfying given U to A in G admissible, the square given by OY of U mapping to OY of A, receiving a map from phi upper star OX of A, phi upper star OX of U. This is a pullback. Okay. And the key feature that Lurie proves is that there is an adjunction of the form spec and global sections. There's a lot rolled into this. So, Lurie explicitly constructs this. Constructs a G spectrum for a geometry G. And what is this functor? This functor says if you give me a pair X, O from G to X, then I can also regard this as an object in sheaves X with coefficients in int G op by the same embedding as above. And gamma sends XO to exactly the global sections of this sheaf, i.e. evaluate on the terminal object. So it's kind of absurd generality. And essentially what we do is we build the Zariski geometry on two rings, prove that it's a geometry, and then this construction gets you the existence of a spectrum for free. It now sort of remains to identify what this spectrum is. And so our next result identifies what the spectrum is in the case of G-zar. So in the case of G-zar, you can identify what the spectrum is explicitly. And so building off of work of Koch and Pitch, Joachim Koch and Wolfgang Pitch in 2017, Huckster duality for Huckster duality and reconstruction of schemes. There's a point for you in there. You can identify, using this work, you can sort of identify what the spectrum is supposed to be. And we show that the spectrum can be identified exactly as the pair of sheaves on spec K, OK. Spec K here is the Balmer spectrum, Okay. So this is the space whose points are the prime thick tensor ideals of K, and whose topology is determined by the loci of prime ideals where certain objects are contained, thought of as their support. And the sheaf OK, regarded as an object of sheaves in Calc, can be identified with the sheafification of the assignment OK twiddle, which sends a compact open of the form UA. This is given by the prime thick tensor ideals of K, such that A is excluded or included in P. And this is a subset of spec K. And maps this to what you think K Karoubi quotiented at A. And furthermore, if K is rigid, then no sheafification was required. You could actually always identify the structure sheaf as the sheaf that you might think it is. Okay. So let me go ahead and stop here for questions before proceeding. Okay, I
So
think I
I
can.
had one little question. When you define the geometry,
Mhm.
do you have to assume it's compactly generated?
Notice that this was kind of elided in some capacity, right? So a geometry itself was a geometry itself was consisting of the small objects, right? And in Lurie's setup, uh, you prove that you move from int g op. So if you had a category and that category was compactly generated, so identifiable as int g op, then you could equip its compact objects with a geometry, and that would give you a way to geometrize the original category that you started with. So yeah, hidden in this is the fact that two rings themselves are compactly generated, which we show early on. Um, and because two rings are compactly generated, to fit them into an adjunction that looks like this, I just had to, equip its compact objects with a geometry.
All right, thank you very much.
Mhm. Okay. Let me go ahead and move on. So the upshot is that the Balmer spectrum carries a sheaf of rings with the same affineness property as the ordinary Zariski spectrum, which means that in particular, mapping between uh, mapping between affine objects. So one thing that I should mention is that a corollary is that if I look at the subcategory of rigid two rings and I look at the spectrum mapping to L top G zar op, then this is fully faithful. Why? Because this sits in an adjunction with global sections and by the identification upstairs you can prove that the global sections like if I apply spec global sections it just recovers the original thing. So the unit is an equivalence and so it must have been fully faithful. And so the upshot is that the Balmer spectrum carries a sheaf of ring with the same affineness property as the ordinary Zariski spectrum, and moreover, mapping between rigid objects is geometrizable, i.e. satisfies gluing. Which means you can try to piece these things together and build potentially non-affine objects, which I'll talk about later. But let's get ourselves grounded with some of the other early theory. So one of the early innovations of sort of the spectrum approach to computing thick tensor ideals was this construction of a comparison transformation, right? From the Balmer spectrum of a two ring to the Zariski spectrum of pi zero of its endomorphism or pi star of its endomorphism, endomorphisms of the unit as a ring. So um, those comparison transformations also fit nicely into this picture. So for that, we'll have to introduce the notion of a morphism of geometries. So morphism of geometries is a left exact functor alpha from G to G prime, which sends G add to G prime add. So it respects admissible morphisms, and it sends admissible covers to admissible covers. So it's a morphism of sites. And one thing that you can show is that, perf, the category which the functor which sends a ring R to its two ring of perfect complexes is a morphism of geometries. And here, when I talk about, recall that G's are, this means calg omega op. And here I really, when I refer to calg, I really mean E infinity. So this does not work if you decided to make this if you decided to refer exclusively to ordinary rings, this does not work. You really needed the E infinity to make this work. Okay. Now associated to any morphism of geometries is a restriction functor. So associated to any morphism of geometries G to G prime is a restriction functor from L top G prime to L top G. How are we supposed to think about this? Well, one way to think about this is I'm just sending a pair XO to the G structure XO circ P. But there's a nicer way to think about this is that if I pass two ind categories, I get an adjunction given by P upper star ind G op to ind G prime op P lower star. And concretely what the restriction functor did, so restriction functor sends X O, now regarded as an object of sheaves X with coefficients in int G op, to X P star circ O, now regarded as a element of this should be G prime, sheaves int G op. Let's do this in the specific example that we care about. In the specific example that we care about, if I look at L top G zar, these guys consist of pairs X and O, a sheaf of two rings on X. And I have this restriction functor L top G Caesar. And what it does is it forgets this to X and O1, i.e. just the sheaf of endomorphism rings. The sheaf of endomorphism ring spectra of the unit, I should say. Okay. So remember that I have my functor given by the Zariski spectrum. So I have two Kelch sitting in here, and I have my functor Zariski spectrum sitting in here, and I have my Cal sitting in here, and I have my functor Zariski spectrum sitting here, and associated to this, I have a functor perf going that way, and I have a forgetful functor given by and I have a forgetful functor given by endomorphism ring spectrum of the unit going either way. Blank of the unit. And so just as a mate transformation, I mean, my comparison transformation is essentially just the affinization. And Balmer already shows this, is if you give me something of the form K living in here, I could pass it to the Zariski spectrum. K living in here, I could pass it to its Zariski spectrum down here. And then I could forget that to an object of L top here. Or I could take the endomorphism ring of its unit. And I could take the spectrum of the endomorphism ring of its unit. And I have a natural affinization map going that way. And locally ringed topoiron, or rather going the other way, because I'm working against the geometric direction. So I have a map going that way, which is exactly, this is exactly Balmer's comparison map. This is the Balmer comparison. So let me talk about something kind of interesting that shows up in this picture. This restriction functor actually admits an adjoint. This adjoint is called a relative spectrum. And this is constructed by Lurie and DAG V again. Any morphism of geometry sits in an adjunction like this. And there's this adjoint called a relative spectrum. Concretely, what does the relative spectrum do? If you give me XOX, and this is a locally ringed topos, let's say, which I'm going to use as shorthand. I mean, locally ringed topoi are the opposite category, but a topos with classical Zariski structure. And I look at spec 2.1, XO, now as an object in topoi with local Zariski structure, then I get an identification between maps in L top G zar from spec 2.1 XO to YOY is equivalent to maps from L top G zar XO into X and O, or just, sorry, XO into Y and O1 of Y. Okay. What it means to be an adjunction, right? So one example, so key example, is that if you give me something that was already affine, something of the form spec R in where R was in commutative rings, okay, then spec 2.1 of spec R is equivalent to the spectrum of its perfect complexes. And what does this encode? This encodes that mapping into the Zariski spectrum of R is the same thing as mapping from R into the global sections of my sheaf of endomorphism rings, which is just mapping from R into the endomorphism ring of the unit, is the same thing as a map from perf R into the global sections, is the same thing as a map into spec perf R. Okay, so this is, you know, chase identifications. And in fact, you can prove, and there's a theorem that I show. You can think of this as an incarnation of the Hopkins-Niemann reconstruction theorem. Okay. Of course, Hopkins-Niemann is also identify what happens on points. Because, I mean, this thing has a natural co-unit mapping back down to spec R once you forget. So Hopkins-Niemann is also identify what happens on points. And that admits a globalization, and the globalization is due to Balmer, and in this language has the following incarnation, and it's the fact that spec 2.1 of X is equal to spec perf X whenever X is qcqs. Spectral scheme. Okay. So what it's actually saying is that if I tried to take an ordinary spectral scheme as like a locally ringed space regarded as a topos with local G structure, and I tried to induce it up to a topos with local Zariski structure, so locally two-ringed space, let's say, then I actually got something affine. So you know, trying to induce up a QCQS scheme actually made something affine. It's an instance of one affineness philosophy. And you prove this as a corollary of the following really interesting fact. So definition, let's try to move beyond, we'll try to move beyond affine two schemes. And we'll try to, you know, describe what an arbitrary two scheme should be in the setting of higher geometry. Two scheme is an object XO in L top G Zar, which is of the following form. One, X is sheaves on a topological space, let's say. I mean, you can also just use sheaves on a frame, but let's be concrete and say sheaves on X for X a topological space. Two, there admits a cover. X admits a cover by affine two schemes, right? So X is equal to union UI goes from 1 to n, where sheaves U O restricted to U is affine, is of the form spec K. Okay. And the theorem that you can show, so there's an observation first that I will say, that any relative spectrum of a spectral scheme is a two scheme. How are you supposed to think of this? Well, a spectral scheme is a moduli problem, right? Mapping into a spectral scheme is concretely, decomposing my space into an open cover, which maps into each of its affine pieces in a manner that glues. So a spectral scheme is a moduli problem. The relative spectrum of the spectral scheme is the same moduli problem, except you glue perfect complexes the same way that you glue the affine neighborhoods, right? So, point is that spec2-1 sends opens to opens. So in particular, we also know that spec2-1 of a qcqs2 scheme, of a qcqs scheme, is a two scheme. qcqs2 scheme. And you can prove the following really some maybe unexpected result, which is that a two scheme is affine if and only if it's qcqs. Note the stark contrast to ordinary algebraic geometry, where most schemes of interest, I think, are qcqs. Right. And so this fact that the relative this reconstruction theorem of Balmer, which says that the perfect complexes on X, admits a map of underlying spaces back down to X, that's an equivalence. Well, that comparison map, this comparison transformation, is coming from this identification. This is just the co-unit map. So the content of Balmer's identification comes down to understanding what happens at local pieces, which is Hopkins, Niemann, and then gluing those pieces together. And that identification is really a consequence of the fact that this is a qcqs2 scheme and thus must have been affine, which is somewhat strange. Okay. As a corollary, you got the following fact that given K in 2-calg rig, mapping from perfect complexes on a scheme X into K is the same thing as mapping spec K with its sheaf of endomorphism rings again, we're not moving in the geometric direction, we're moving in the L-top direction. Just a map from X into it. So it's a new universal property for perfect complexes on X, where X is a qcqs spectral scheme. And such maps abound, is probably what I'm going to end on. Actually, Rudradeep, do I have till the hour?
Yeah.
Okay, cool. And so here's a key example. Is that if you give me G, a finite group, and K, a field of characteristic P, you can consider its stable module category still kg, and the Balmer spectrum of the stable module category kg, equipped with this structure sheaf of endomorphism rings, is a qcqs spectral scheme. And so in particular, if I define this qcqs spectral scheme to be VG, the spectral support variety, then a consequence is that there exists a unique map, there exists a canonical map, excuse me, from perfect complexes on VG into the stable module category of KG. And you can show that this is an equivalence onto the principal block. This has its precursor in work of Balmer, where in a paper in 2008, Balmer writes a way to construct endotrivial modules in the stable module category of G by relating them to line bundles on the classical support variety after you invert P. And it's a co-cycle construction that is somewhat ad hoc. But it's a shadow of this fact, which yields it to you naturally in G, which you didn't know beforehand for Balmer's result. And so in particular, you can use this to say things about endotrivial modules in StickKG. You can compute a thing about endotrivial modules in the principal block, which unfortunately won't be able to get to today. But as a final example, I'll indicate that there's also this newer work of Balmer-Gallauer and which proves that for E an elementary abelian group, that if I look at the spectrum of the category of permutation modules of E over a field K is Ker P, that this is a Dirac scheme. In fact, that's a shadow of the fact that spec, or directly implies, in fact, that spec KEK equipped with its sheaf of endomorphism rings is a Dirac spectral scheme. It's a Dirac spectral scheme, suitably defined. And the theorem upstairs will also work in this generality. So if I decide to call this maybe the permutation support variety, then there's a map from perf VE perm into KEK, functorial in the group. Okay, yeah, I didn't get to applications, but that's okay. I will stop here.
Thank you, Anish. Let's all give the speaker a round of applause now. If there are any questions for the speaker, if you have any questions for the speaker, please ask them now. If we go back to the well, maybe in the last page when you were getting back classical Hopkins-Riemann result.
Yes, okay, here, right.
So, I mean, is there any hope of getting back the thick subcategory theorems of Akil for TMF?
Yeah, absolutely. So what Akil, so for a regular even periodic, like a locally regular, locally even periodic spectral scheme, then then you can get back those results essentially by using the same argument. Like so you have this comparison map to X, and you just have to check how the comparison map behaves locally. And you can, find out what happens locally by using the first part, like what happens in section 2 of this paper, where he identifies this by constructing residue fields. The descent that he does is a little bit more sophisticated because he's also doing it for something structured on a spectral Deligne-Mumford stack. So he has to do étale descent. And that's in general kind of bad, but what you can show is that it's not so bad in this particular instance. There's like a horizontal vanishing line and the descent spectral sequence. And you can sort of use this to control the production of classes that'll realize certain closed loci. And so this is something that I'm actively exploring, is what if you decide to take a locally ringed topos that was not a scheme? So for example, you could do the following thing. You could take a spectral Deligne-Mumford stack, and this thing is a perfectly good example of a locally ringed topos. And you have a comparison map from spec 2.1 of X to spec perf of X. And in fact, this is the affinization map. You can prove that this is the affinization map. And this sort of precisely encodes the failure of the Balmer spectrum to satisfy descent. Now, you didn't have to do it in this language, because what you could have done instead is you could have, sheafified the assignment that sends a ring to the Balmer spectrum of its perfect complexes, and then you could have constructed this map sort of slightly differently. But there's something nice about this map in that it's structured. So the fact that there's a horizontal vanishing line for the descent spectral sequence is encoded in something about the pullback morphism being nilpotence detecting, being actually descendable, if you like, nilp detecting, even descendable. So you could honestly do, I mean, again, recovering his thick subcategory theorems involves basically unpacking the descent problem, but you could ask yourself, what if I decided not to work with, topoi that really came from algebraic geometry, right? Because again, you could do this with like, something that was like an FPPF stack, and then you could construct a comparison morphism that encodes the descent, but you didn't actually have to use topoi that came from algebraic geometry in some sense. So for example, you could take like, as long as your ring satisfied descent over some topos, you could still construct this comparison map from spec 2.1. So yeah, I don't want to hold people up too much longer, but there's something that I'm exploring where you can try to compute like the Balmer spectrum of perfect complexes over K-theory by stratifying it over the Nisnevich topos. Or you could try to do what Balmer does, where he approximates the stable module category by a growth and decay that's based on the orbit category of G. And all of this is perfectly fine to do. So it doesn't recover them, but it gives you slightly different avenues for systematizing similar kinds of arguments.
Just one small comment. I mean, when you said even periodic, so TMF is not even periodic, but still even locally, you will go down and use the modular step of elliptic curves and all that.
Yeah, it's locally regular, even periodic. Yes.
Thank you. Any other questions? And the last few results, which were just C, so those will be in the paper that will get archived next week.
Yes.
That's not in the paper that's already out.
Yeah, that should hopefully be out next week. So these constructions will also be listed over there. And then the applications to endotrivial modules will hopefully be in a follow-up after.
Yeah, and actually, I mean, Gregory Kendall has done some work in computing the Balmer spectrum of stable model categories of some kinds of infinite groups. I think this example carries over somewhat, although I'm not so sure about the support variety part. But anyway, I think anyway.
But yeah, if you could send me some of the references, that would be great.
Gregory Kendall, Kendall.
Got it. Thank you.
Any questions? Anybody? Somebody asked if you would be fine with sharing the notes afterwards.
Yeah, I can email them to you.
Okay. There's a question in the chat. Can you have a look, Anish?
Yes, you are able to interpret the Balmer comparison map to the homogeneous spectrum of the graded endomorphism ring of the unit. And so you just have to work with a slightly different geometry. The classical Zariski geometry only inverts elements in pi 0. And you could work with the Dirac spectral geometry where you're allowed to invert elements in pi star as well for your admissible maps. And then you make your admissible covers like things that jointly generate the unit ideal. And then it works fine. So yeah, and we do this in the paper as well.
Thank you, Jean-Paul, for the question. Okay, we don't have any more questions. Maybe we should let the speaker go catch his flight. Let's thank Anish once again.
Thank you very much for the talk.
Thank you.
Thank you very much.